Hello everyone, welcome to this presentation where we are going to talk about how to create our own version of a numerically controlled oscillator for FPGA. We will make use of a Python package called Amaranth. During this presentation we are going to see what a numerically controlled oscillator is, and then we'll take a look at the principle to implement an Amaranth version of a numerically controlled oscillator. So first of all, what a numerically controlled oscillator is. You could see it as an electronic circuit with two inputs and one output. The first input would be a frequency written over n bits and a clock signal. And the output of an NCO is a bunch of wires that are giving values for a discrete version of a sinusoid signal, which frequency would be equal to the frequency we gave in input. So how are we going to implement this with Amaranth? Well, we need to reproduce a sinusoid. So let's take a period of a sinusoid, and as we need to make it a discrete sinusoid, we will take integer values between, for example, 0 and 255. The second step, after having decided on which range we are going to output the sinusoid signal, is to store the values of this sinusoid signal inside a memory. For example, if we take a memory with 8 different addresses, we can store 8 values of the sinusoid signal, and then we will walk through the memory to output separately all the values that we are reading in order to recreate a signal that looks like a sinusoid. So how do we choose the speed at which we are traveling through the memory? In order to travel the memory, we are using something we call a phase accumulator, which is just in fact a register that we are going to increment with a certain step. Every time you receive a clock signal on the clock input of the NCO, you are incrementing the value of the accumulator by adding the value of the step. So it goes like this, and as you can see, every time I'm adding a step, we are walking through the memory one place. If we take a value of step that is twice as big, we would go through the memory twice as fast, and so it would give us a sinusoid signal with a frequency 2 times greater. When we reach the end of the memory, if you just add the step once again, you create an overflow, and when you are overflowing, you come back to the beginning. So that's exactly what we want, because we need to repeat this sinusoid period several times while we are running our program. So you may wonder now, how do I choose the step? Well, you should choose it in respect to this formula, because the principle is to overflow every time we have waited a certain amount of time, and the certain amount of time you need to wait is given by the difference between the clock frequency you have in input and the clock frequency you wish to output. So it gives us this formula, and to decide for the step you just need to make some operations, and it gives you a value for a step which is the maximum value of the accumulator multiplied by the output frequency and divided by the clock frequency of the FPGA. And the beauty of this approach for recreating a sinusoid signal is that, in fact, you can output any form of signal. Not only sinusoid, but for example, if I take the identity function, it would give us a square function, a triangle function for the signal we are going to output on our NCO, and the principle remains the same. Alright, so now let's see how to implement such numerically controlled oscillator on Python. First of all, we need to make a few imports to make sure that we have all the tools we need. So here, of course, we need Amaranth. We will make some simulations, so Amaranth Sim is also imported. We are going in this presentation to use some graphics, so we need to use Matplotlib and NumPy, and then the mathematical tools we are going to use are the cosine function, the value of pi, the CL function and the logarithm base 2. And once we've done this, the first thing to do is to define the function that will make discrete our sinusoid function. So let's, for example, create the cosine function for values between 0 and 255. We will make this for x, and we also need another parameter, which will be the maximum value the function will expect to get as x. Then here we make a variable which will be our result. It will be the value of the cosine function applied to x times 2 times pi and divided by x max value. We plus 1 this thing in order to have a function that is not between -1 and 1 but between 0 and 2, and then we divide it by 2 to have a function that is between 0 and 1. Then we multiply it by 255, and then we say that the result in fact should be an integer. So this will be int of res. And now we return res. Now we can test it. Let's say we are going to give to our cos255 function values between 0 and 2048, for example. So the max value will be 2048. And as we are going to plot this with matplotlib, we will also make not only values for x but for y. And here we are. So now that we have the values for x and y to plot, and we should be good. So now let's try this. Oh, we forgot to mention that here we need to specify the value of the maximum. Nah, didn't save. And here you see that you have a nice cosine function with values between 0 and 255, and that those values go from x coordinates 0 to x coordinates 248. If you zoom on the graphic, you will see in fact that those values are a discrete one and not continuous. So that's exactly those values that we wish to save in the memory of our FPGA. Now we can do the same for the identity function. Identity 127, for example, because we are going to output the values of our identity function between 0 and 170 and 127. And that's it. So now if we replace this function by identity 127 and we run the program again, we get a nice identity function that will give us just one period of signal, and so we expect with this function to output a triangle signal. So now that we're done with the function we wish to save inside the memory of our program, let's write the program, the description of the numerically controlled oscillator. So as usual, we create a new class which we'll call NCO, which extends the class elaboratable. We define a constructor, And the question is now, what are the parameters we need to give to the constructor? First of all, we need to know what is the frequency of the FPGA for the clock. So FPGA clock. Secondly, we need to know what will be the size of the memory we are going to use to store the values we calculate with the functions just above. So parameter mem size. Then the question is, which function are we going to use for the values that we wish to save inside the memory? Then we need to tell the minimum input frequency that we are going to ask the numerically controlled oscillator, the maximum input frequency, and lastly, the max value of the output. So these are both the parameters of the NCO and the parameters of the function we are going to use in the memory. Let's define the accumulator. To define the accumulator, we need also to specify what is its size. We wish to be able to recreate a signal which frequency would be, for example, only 1 Hz. And to do so, we need to have a size that is big enough to hold the number of clock signal to receive before 1 second has passed. So we need at least this to be log of the FPGA clock, which is the clock frequency, because if we can count up to the clock frequency, then we are able to recreate a signal with a frequency 1 Hz. And we also need to know what is the minimum frequency that will be asked to the NCO, because if this way we are able to recreate a signal with a frequency 1 Hz, but if we ask for a 0.5 Hz frequency, then this accumulator is not big enough, and so we need to take back from this log of the minimum input frequency. Then we define the accumulator, which is a signal of size accumulator size. Here I forgot to mention that we need to round up the value so that it's an integer, because we can't give 2.5 bits signal here. It would make no sense. And now we are done for the accumulator definition. Let's define the output. So first we need to define what is the size of the output, because we are going to use it later in the program. So now we are going to define the output and the input of our numerically controlled oscillator. Now we need to define the shape of the signal we will save inside the memory. So x is equal to I for I in range, the memory size, and y is for the moment nothing. So we'll fill it up the same way we did for our test just below, and we use the function given in parameter. So this will be a function of I, and the maximum value here is max output val. And now that we are done for this, we are going to store this in an Amaranth memory. Its width is the output size. Its depth is the memory size. And finally, we will init the memory with the values of y. We're done for the memory. Now we need to specify what will be the size of the addresses. And we're done for the initialization. Let's define the elaborate method. As usual, we define a module. We define a step signal, step which is equal to a signal of size the same as the accumulator. Then we can add some rules. So the combinatorial rules are the value of the step and the value of the output. m.domain.combinatorial, and the rules we add are step.equal the value of the input and self.output equals the value we store in the memory at the address, which is equal to the value of the accumulator, but we only need to read on the n last bit, n being the size of an address in the memory. So here this is self.addr size. We take those n last bits, which will be the value we take from the accumulator, which is the value we use as the address for the memory to output in the VCO. Now we're done for this, and the synchronous rule is that the accumulator is equal to the accumulator plus the value of the step. So now we're done for the VCO. However, our numerically controlled oscillator is not operational yet. There are a few things to change, and first of all, there is a correction to apply to the value of the steps we make. Because here, when we decided what size would be the accumulator, we did a rounding operation. And by rounding this value, we are making the minimum input value not equal to the one we give in parameter, but one that could be much lower due to the fact that the accumulator would have been rounded up for the number of bits it is using. So we need to correct this thing. As we will not correct the size of the accumulator, we need to correct through a parameter that will a correction parameter that will multiply the step following the value of the accumulator. Here we calculate the true value of the minimal frequency we are able to recreate. So it depends only on the FPGA clock and the size of the accumulator. We define the correction factor. So we set it to 1 in case we need no correction to apply, and then if the actual minimum frequency is lower than 1, that means we did a rounding, and so we can correct it by defining a new value for the correction factor. We need to round it once again because we are only able to use integer values for our operations within the FPGA. But we can hope that this would be enough anyway to make a great correction. And so once we've done this, let's correct the step. And here we are. So now let's write a new main function to simulate our FPGA. So we gave an FPGA clock of 48 kilohertz. We say that the size of the memory will be a kilobyte. The function that we are going to use will be, for example, our sinusoid, so it's cos 255. The minimum input frequency we would ask would be the hertz, and the maximum input frequency would be, for example, 600. And the output max value would be 255. Let's create a new device under test, which will be a new instance of an NCO with all the parameters defined above. Let's create a new simulation, then define a procedure to accomplish while running the simulation. First of all, we are going to see if the values we stored in the memory are correctly presented. And once this is done, we are just going to simulate, for example, the fact that we asked our numerically controlled oscillator to have as input a certain value, for example, an A, the music note, let's write a B, and a C, and here we are. So now let's just run this. Here at first it looks like the values we stored in our memory are well representing a sinusoid signal. So if we zoom in, for example, at the beginning, you see all the steps, so that shows that inside the memory several addresses contain the same value for the beginning. Here it seems to be fine for the memory. Now the program was running the test, and we can now look at it with GTK wave and see what the signal looks like in the end from the output point of view. So we can look at the accumulator signal, the clock, the input. Here all the values that are stored in the memories. For example, here you see it's FF, just as in the graphic. Here you have FE, so several times the signals have the same value, and here F5, F4, etc. So let's see the step we make following the value of the input and the output value. We will output the value as an analog signal. The step will be written in binary and the accumulator in binary too. The input is decimal format. So here we have an A, and let's see what the output looks like. So if we zoom out enough, we can see the waves, which is fine, and you see that the accumulator is changing its value every time there is a clock rising edge, and that this is allowing us to change the place where we are reading the values inside the memory. So we have a nice sinusoid signal, and let's see if here the period corresponds to what we expect it to be. We ask for a frequency of 440 Hertz. Here we have 3100 microseconds. if we ask Python if this is the correct frequency, and it looks like, in fact, the frequency we are outputting right now is not exactly 440, but something smaller. So there must be a mistake somewhere, and the mistake comes from the fact that our accumulator size is not big enough. We need a much greater accumulator to hold values with even more precision for operations to be made. So here we are going to define a gain, and we will totally arbitrarily define it to 10, so that here the size of the accumulator is the gain. And by doing this, we are improving the precision at which we can define here the values we have at the end of our steps, so that the carries, every time we make the operations, hold more information about when the signal should change. So now that we defined this, let's exit and try once again. So we run the program. Here we still have a nice sinusoid, and if we run GTK wave, so the accumulator has more bits than before. The input doesn't change. And we are going to look at the output. So when zooming out, we see that here the cursor is at 2260. So let's try again with Python. And we have a value which is much closer to what we expect it to be. So that's how you correct it. And here you see that the three different values we gave are displaying differently because of the fact GTK wave cannot be as precise when we zoom out. And so it shows us that the frequency is well changing between the different states of the NCO. So that's it for the principle of the numerically controlled oscillator. You may wonder what it looks like when you replace the function, the sinusoid function, by an identity function. Well, let's do this, and then we'll leave. So here we change this function for identity 127. We save. We run it again. Well, there's nothing so surprising about what we are going to see, but here, bench, top, output, and we get a triangle signal. So here you see that this signal is repeated every time we are overflowing. So in the end, thanks to this tutorial, you had the occasion to see how a numerically controlled oscillator works, and you could also see some of the challenges you meet when you need to implement one on your FPGA. Thanks for listening, have a nice day, and see you probably in another video.